Hi class, welcome to the next section, chapter 6.4. Today we're going to focus on curve sketching. So we have done a lot of new stuff in this class so far. This is the section where we're going to put it all together in order to really analyze a function. So with all the tools that we have so far from calculus, we really should be able to sketch or graph any curve by hand. Right? Now you might be saying, Professor Williams, why would I want to do that if I have Desmos and all these other things? Sometimes it's not about sketching the curve, but more so understanding how we can use calculus to analyze our function, right? So if we put it all together in one section for curve sketching that we're going to do now, it kind of reiterates what it is that we've been doing and how we can use calculus to analyze all the different facets of our graph, right? So in this section, we're gonna put everything together and using calculus, and then use all the information that we gather from a function, and then use it to sketch our curve. So if you've taken pre-calc with me, you've seen me do this for rational functions and polynomials, but without the calculus portion involved, right? So using calculus, we should really be able to graph a curve pretty much exactly. When I say pretty much exactly, really, it means that we can include all the really important pieces of our graph when we sketch this, right? So it might not be an exact sketch of our graph, but all the important pieces will be there in this sketch. Right, and so that's what we're going to do today. Is we're going to use calculus to analyze a graph, and then we'll just put it all together. Okay. So we're really going to just have one example. We'll just take one function, somewhat of a difficult function. Here we have natural log of x squared minus 9. So this isn't like a standard, I don't know, like exponential function where we've shifted it up and down to the left or to the right and stretch it in some way. This is a composed function. It's a function inside of a function. So graphing this would be difficult if I just ask you to graph it by hand, right? So we're going to go ahead and we're going to go through all of the important parts of a graph and find out what those things are, and then we'll just put them all on a graph and then draw our lines as necessary, right? So if I want to draw any graph, not just this graph, but any graph accurately, I need to know where the y-intercept is, okay? I need to know all the x-intercepts, or lack thereof. I need to know all of the vertical asymptotes, if there are any. I need to understand the horizontal asymptotes, the long-term behavior, what is happening at infinity and negative infinity. So here we'll look at limits. At my vertical asymptotes, I also need to look at limits. What am I doing as I approach from the left and from the right for my vertical asymptotes? What are the maximum and minimum values, right? Specifically, what are the local maxes? What are the local mins? Obviously, we're not graphing this on a closed interval, so I'm not looking for absolute maximum and minimums, but I'm looking for any localized max and min values. What are my intervals of increase and decrease? And what are my intervals of concavity? When is my function concave up? When is my function concave down? So just looking at this, all of these things have kind of had their own section dedicated to them. Not so much the x and y intercepts. Well, the x-intercepts we have, especially for functions, for polynomials, right, are factoring, all of our methods for factoring polynomials. So we had a section dedicated to x-intercepts. We had a section dedicated to vertical asymptotes and horizontal asymptotes. We've had a section or two dedicated to localized max and mins. Intervals of increase and decrease were also in that section for max and mins. We've actually been talking about intervals of increase and decrease throughout the course since chapter 3. Then intervals of concavity had its own section as well, right, when we're talking about second derivatives in the last section. So all of these we've looked at independently. So at this point now, we're literally taking everything we've done in the course up to date and putting it all together. Okay, the only thing that's not in here is Noon's method, which actually it is. We could use Noon's method to find zeros and x-intercepts if we're not able to factor. But what we don't have, the only thing I'm not seeing is the differentials. Okay, we're not talking about differentials here at all. That's really the only thing that's kind of left out, right? So let's go ahead and start. Okay, we're gonna go in order. So the y-intercept, that's easy. That's what happens when x is 0, so there's no left or right movement. Where am I on the y-axis? So I just plug in 0 for x. Okay, x equals 0 is how I find my y-intercept. So when I plug in 0, I'm going to have natural log of -9. Okay, which means that I don't exist. I don't have a y-intercept. Okay, I'm never ever going to cross the y-axis or have a value that's on the y-axis. So that's good to know, right? There is no y-intercept, which means I'm probably going to have a vertical asymptote somewhere, right? Well, I definitely will, but so there's no y-intercept. My x-intercepts. So for x-intercepts, I set my function equal to 0, right? Y is 0. There's no up or down movement, only left or right movement. So 0 equals natural log x squared minus 9. So in order to solve this, I can raise both sides to e if I want to. Right? If I do that, that brings this to x squared minus 9. This equals 1. Or I just understand that natural log equals 0 when the inside is 1. Either way, it'll work, right? Either way, I kind of get the same thing. So I need to solve this equation then. So basically, I'm solving x squared minus 10 equals 0, which has solutions of plus or minus square root 10. Okay. So for 3, we're looking at vertical asymptotes. So now I'm going to be looking at things that I'm not allowed to plug in to my my function. So it would be nice to know what the domain is for that, right? Okay. So my function on the inside is never allowed to be 0 or less than 0. So that's the restriction I have for my domain. You can't plug anything into natural log that is less than 0, right? 0 or less. So I'm not allowed to be the values -3 or 3 or any value in between there, right? So when I plug in a value in between -3 and 3, this value will be negative, right? So for instance, if I plug in 0 here, I get out -9, right? So that's how I know I can't be on the inside of the 2 zeros of this function, right? So x equals +3 and -3 are vertical asymptotes, and I will have nothing existing in between these values because this is outside of my domain, right? So for 4, I'm going to be looking for the horizontal asymptotes, the long-range behavior. So I'm looking at what my function is doing as x goes to infinity or -infinity. If it's hard for me to look at, depending on the form of the equation that I have, I may have to use L'Hopital's rule to look at that, right? Here we don't have a ratio, a function, so I don't really have to worry about that, okay? But we can look at this and say, well, what happens when I plug in very large negative numbers? So if I plugged in like -1 million, for instance, what does this do? I get out a large value, okay? It's the same thing as if I plug in a very large positive value because my x's get squared. So my left side end behavior and my right side end behavior are the same. So the limit to -infinity and the limit to infinity are the same. They both go to infinity as I go to the extreme values, okay? So 5 is looking for my max and min values. So remember, there's 2 ways to do this. Okay, so my max and min values. So the 2 methods are the first derivative test or the second derivative test. I think that no matter what, we have to find the second derivative because the last thing we're going to look at are our intervals of concavity. And in order to find the second derivative, well, guess what? I got to find the first derivative, right? So I think the second derivative test will be the most useful because I'm going to end up finding my intervals of concavity using that value anyways. However, the first derivative test is fine as well. So remember, if I do the first derivative test, that means I'm finding my critical values and then I'm checking what my derivative is doing to the left and to the right. So the nice thing about the first derivative test is it'll also tell me my intervals of increase and decrease. So that's useful. If I do the second derivative test, I already get my first derivative, and then I can use that second derivative to look for my intervals of concavity. So it's kind of a wash. It doesn't really matter which one I decide to choose because I gotta find both derivatives anyways, right? So let's come here. So max and min values. So taking the derivative, I will have 1 over the inside function times the derivative of the inside function. So 1 over x squared minus 9 times 2x. Okay, so that's my derivative. Simplify that. It's 2x over x squared minus 9. I would like to know when this function is 0 or any undefined values, right? So I have vertical asymptotes for the derivative at x equals 3 and negative 3, which is fine. I already know those are asymptotes, so I'm definitely not going to have any max or mins there, so I don't even have to worry about those values. It looks like my other possible max or mins is at x equals 0 because that's what makes the numerator 0. But guess what? 0 is not in my domain. I'm not allowed to plug in any value in between negative 3 and 3. So I don't have any max or min values. Okay, so my critical values are 0, plus 3, and negative 3. I have to check the signs around these critical values. I just informally showed you that none of these are an option because 2 of them are asymptotes and then 1 of them is not in the domain. So I actually don't have to do anything from here. But if I did have values that were applicable, then I would check the signs around those values, right? But again, here notice that all of these values are restricted. So none of these are even in my domain. So I can't even use them. Okay. Again, here the domain includes negative 3 and 3. So all of these are not in the domain. So I have no local max or min values. Okay. So now I need intervals of increase and decrease. So I already have my first derivative. So I'm just going to take values like I wanted to do for max and min and check values around the absolute value, the critical values. But since I don't have those, I just need to look at this function, 2x over x squared minus 9, and I just need to figure out when is it positive and when is it negative, right? So that's what I need to do. Easier thing to do is just check a single value that's on the left of the smallest value that's restricted in the domain and check a value that's on the right of the largest value, because then I can just see is it positive or negative, because my function has zeros at square root of 10 and negative square root of 10. So I'm using this, right? So I just need to look at this function. So it's either always positive or always negative because the derivative doesn't have any zeros that are in my domain, I should say, right? So I just need to check the values here. So that's why I'm going to check negative 4. So when I plug negative 4, I get a negative on top and a positive on the bottom, right? Because negative 4 times 2 is a negative. When I plug 4 in here, I get 16 minus 9, so that gives me a positive. So I get a negative value. So I'm decreasing on one side from negative infinity all the way up to that asymptote of negative 3. Okay, I'm going to check 4 on the other side, and I get plus over plus, which gives me plus, which means I am always positive. So checking my signs, I got a negative here. This is not applicable. This is not applicable because I don't have any values inside of this interval. And on this side, my first derivative is positive. So I'm decreasing from negative infinity all the way up to this point, and I'm increasing from 3 all the way to infinity here, right? So those are my intervals of increase and decrease based on the first derivative. Okay, and last we need to find our concavity, right? Our intervals of concave up and our intervals of being concave down. So I need to find the second derivative. So remember, my first derivative is 2x over x squared minus 9. So the second derivative is the quotient rule on that function. Okay, this is my first derivative. So using the quotient rule, I'm going to have 2 times x squared minus 9 minus 2x times 2x over x squared minus 9 squared. Okay, so using the quotient rule, so 2 derivative of the first, leave the second alone, subtract from that the first being left alone, the second being differentiated, and then squaring the bottom function. Simplify all these things, right? I got a 2x squared minus 18 minus 4x squared. Okay. So when I combine those together, I end up with a negative 2x squared because I had a 2x squared minus a 4x squared. Here I can pull out a negative 2. Okay. And that doesn't simplify anymore, but I do need to check for when these things are concave up and concave down. So again, I'm checking the important values. My denominator here has the same exact zeros as before, plus and minus 3, and I don't exist in between those, so I don't even have to worry about this denominator. I just need to know when this numerator is 0, and then I need to check the values between that so that I know when it's positive or negative, right? So plus and minus 3 are my possible inflection points, because when I solve this, that's what I'll get. Set this equal to 0, and I have negative times 2x squared plus 9. So try to simplify everything. So you can also think about it as I'm adding 18 divided by 2. So technically I will have some square roots here, but it doesn't matter because the values of interest to me that make the denominator 0 are not in my domain. Okay, so I have no inflection points. So I just need to know when is this positive or negative. So same thing again. I'm going to check a value on one end of my asymptote. Again, this plus or minus 3 comes from the bottom because the numerator just gives me complex values, right? Imaginary values, so I don't have to worry about that. So same thing, I'm just going to check the sides on the left of my domain and on the right of the domain, my domain, like I did for intervals of increase and decrease, to see if it's plus or minus so I know when it's concave up and concave down, right? So when I plug in negative 4, something on the outside of negative 3, I get a negative over a plus, right? Because 4 in here is positive, and then it changes signs. So overall it's negative. Same thing's going to happen when I plug in 4. When I plug in 4 here, I'll get a positive value on top, and then a negative 9. Everything on the denominator is squared, so no matter what, it's always going to be positive. So I am concave down everywhere that I exist, right? So on this side of the domain and on this side of the domain, I'm concave down, right? So everywhere that my function actually exists, it's concave down. So before we throw all this together, let's summarize all this, okay? I don't know if it's here, okay? It doesn't matter. But let's summarize all of this real fast, okay? Because that's what we need. I have no y-intercept. My zeros are plus or minus root 10, which is a little bit more than 3, right? Square root of 9 is 3, so square root of 10 is a little bit more than 3. So a little bit more than 3 positive and a little bit more than 3 negative. I have vertical asymptotes at plus or minus 3. My function goes to infinity on both sides, right? Long run behavior as I go to infinity and as I go to negative infinity. My maximum values, I don't have any maximum values, okay? So here there are no local maximum or minimum, values. Intervals of increase and decrease, I am decreasing as I approach negative 3, and I'm increasing as I leave 3. And I am concave down everywhere, right? Concave down everywhere. So just to summarize this, no y-intercepts. My x-intercepts are just a little bit past plus and minus 3 at square root of 10. I am concave down everywhere, okay? Concave down everywhere. There's no inflection points. I'm never changing concavity because I'm always concave down. I'm decreasing in value as I come from this direction. I'm increasing in value as I move away. This goes off to infinity as I move in the negative direction, and this goes off towards infinity as I move in the positive direction. And that's everything, right? So we analyze this entire graph using calculus. Now, would I be able to know the exact values here? No, of course not, right? But I could have drawn this very, very generally. I would have drawn my my vertical asymptotes, and I would have been like, oh, concave down, right? And I go off up, right? Concave down, I approach my vertical asymptote, and I go off. Now, I wouldn't have the exact values mapped, because here I actually, graphed it. But if I wanted to be more accurate, I would plot points along the way, right? I'd actually plug in, like, oh, what happens at -6? Oh, I don't know. Let me plug that into my function and see what I get out, if I want to be super accurate. But really, the point is being able to look at what it is that we're doing using calculus to our function and being able to interpret those things, right? So when I look at a function, I can look at it and say, I might not know what this function looks like, but hey, I know I have some asymptotes at ±3. I know I'm going to go off to infinity just by thinking about what the limit is, what the zeros are. If I take its derivative, I can say, okay, I'm not going to have any maxes or mins, so, that means this or this means that, right? Then I can just use those things to think about what my function is doing as I do math on it. So we've done this a few times where as we go through and calculate things, you have to kind of be a little intuitive about your function and say, oh, I know this about my function, so that means this, right? So for instance, when we're doing the unit circle and we're finding when the tangent line had a slope of 1 on the unit circle, we had to understand that this is going to happen at 2 different points, right? So we were given 4 different possible points where the slope could be 1, but only 2 of them made sense. So we had to use our intuitiveness about a circle to say, oh, these are when the slope's going to be positive because of the angle of the tangent line when it's touching the circle at this point. So same kind of thing. It's nice to have a general intuitiveness about your functions as you work with them, and understanding how calculus tells you about your functions is very, very important, especially if you're going to be a math major. Moving on to courses like real analysis, where you're not drawing a graph for everything, you're just analyzing it using mathematics.